lesson will cover the acids and bases section in the chemistry syllabus. So when we talk about an acid and a base, in matric it is defined by the Lowry-Bronsted model. Now, in order to understand what an acid and a base are, we need to understand what a proton is. A proton is simply an H atom without the electron. So it has been stripped of its electron and it is indicated by an H+. Now that is a proton. So when we refer to an acid in terms of the Lowry-Bronsted model, we refer to an acid as a proton donor. That means that an acid gives away its proton. When we refer to a base, we refer to it as a proton acceptor. That means that a base will accept a proton. Now the proton donated by the acid is then received by the base in an acid-base reaction. Acid-base reactions are also called protolytic reactions. Now in this example over here, which is a simple example, we have HCl and H2O in a reversible reaction forming Cl- plus H3O+. HCl is now an acid as it donates its H+ to the water. The H+ is then donated, leaving us with a Cl-, as we can see here, and the H+ is accepted by water, which acts as a base, and we get H3O+, which is known as the hydronium ion. Hydrogen atoms contain only one proton and one electron. When losing an electron, the hydrogen atom ionizes and a proton remains. So as I was saying earlier, H+ is simply a hydrogen atom that has lost its electron. If we look at the second example over here, we have NH3 in a gas form plus water, forming NH4 plus OH-. In this case, NH3 is the base and water is the acid. As we can see, NH3 becomes NH4, meaning it's accepted in H+, meaning that it's a base, as a base is a proton acceptor. On the other hand, H2O becomes OH-, meaning that it has lost an H+, meaning it's donated it to NH4, and therefore H2O is an acid. In the examples above, water, we can see that water acts as an acid and a base, and substances that can act as both an acid and a base are known as amphiprotic, amphoteric, or ampholytic. Common ampholytes are HCO3-, H2PO4-, HPO42-, and HSO4-. As we can see here, in this example over here, H2PO4- plus H3O+, H2PO4- acts as a base as it accepts a proton. Whereas in this example, it acts as an acid as it donates a proton. Acid-base reactions are reversible. So we have something known as a conjugate acid and a conjugate base. As you can see here, we have water, H2O, and we have H2SO4. Now H2O is a base. It accepts a proton as it becomes H3O+, whereas H2SO4 is an acid as it donates a proton and becomes HSO4-. However, in the reverse reaction, we can see that they are opposite. This has now become a conjugate base, as HSO4 then becomes H2SO4, meaning it's accepted a proton, an H+, meaning it's a conjugate base, and H3O+ becomes H2O, meaning it's donated an H+, giving it the status as a conjugate acid. Next, we move on to acid strength. So if we look at this example over here, we have water plus HNO3 in a reversible reaction forming NO3- plus H3O+, which is the hydronium ion. Acids, when placed in water, donate their protons to water. Water is decomposed in this reaction. As you can see, water is decomposed to H3O+. This is known as hydrolysis. So some acids are better proton donors in water. So a strong acid would be one which is a better proton donor. So if we look at HCl, which is a strong acid, you will need to know that HCl is a strong acid. If we put it with water, we get a reversible reaction where we form H3O plus, where HCl has donated its proton, plus Cl minus, and we form ions H3O plus and Cl minus. This equilibrium lies to the right, as the acid is almost 100% ionized due to the fact that it is a strong acid. When we refer to ionization, it's a molecular substance that produces ions in water. When we refer to dissociation, it's the splitting of ionic compounds into its ions. Next, we move on to the equilibrium constant for an acid. Now, if we look at this, we have HCl plus H2O forming H3O plus Cl minus, which is the same equation as we have over here. When we work with the equilibrium constant, as we do with any other constant, we exclude liquids or solids. So we would exclude H2O as it is a pure liquid, and our equilibrium constant for the acid would be H3O plus, our product, Cl minus, our product, over HCl, and these are obviously all the concentrations of these substances. A strong acid will have an equilibrium constant greater than 1,000. That is just an unspoken rule. If you get a Ka, your equilibrium constant for an acid greater than 1,000, we know that it is a strong acid and it will ionize almost 100% when placed in water. If you have a weak acid, your Ka, your equilibrium constant, will be very small, and that means that it does not ionize fully in water. There will be fewer ions in the water solution. Now, if we look at strong acids and weak acids, these are things that you will need to know. HCl, hydrochloric acid, you will need to know is a strong acid. H2SO4, sulfuric acid, you will need to know is a strong acid, as well as nitric acid, HNO3. Whereas weak acids, which are ones which will not ionize fully in water, are hydrofluoric acid, phosphoric acid, sulfurous acid, and ethanoic acid. Now, if we look at the strength of a base, we look at this example over here. H2O plus NH3 forms NH4 plus, NH3 has accepted a proton, plus OH minus, which is the hydroxide ion. NH3 accepts a proton, meaning it is the base, and H2O is the acid, it donates a proton. In this example over here, we have NaOH plus an aqueous solution forming Na plus OH minus. This is dissociation. An ionic substance has broken down into its ions in an aqueous solution. NaOH is a strong base. Solution consists largely of ions. Due to the fact that this is a strong base, it dissociates almost completely in solution, meaning that the solution will possess a lot of ions. A base that dissolves in water to form OH minus is known as an alkali. That is just something that you will need to know. When we look at an equilibrium constant for a base, we calculate it in the same way that we would for equilibrium constant of an acid. If we look at this example, our equilibrium constant for the base, we do not have a denominator because our reactants are solid and a liquid, therefore we have no denominator, and our products are Na plus and OH minus. A strong base will have a very large Kb value, and a weak base will have a very small Kb value. In the same way, a strong base will dissociate almost completely in water, and a weak base will dissociate only partially in water. Now, you need to know that group 1 hydroxides are strong bases. So any group 1 hydroxide that you are given, you may assume that it is a strong base and will act as a strong base. Polyprotic acids are acids capable of donating more than one proton. If we take a look at these examples, H3PO4, H2SO4, H2C2O4, and H2CO3 are all polyprotic acids. Looking at this example, we can see that H2SO4 plus water, this H2SO4 donates a proton, meaning it's HSO4 minus plus H3O plus. This HSO4 minus will undergo another reaction with water, donating another H plus, leaving it as SO4 2 minus plus H3O plus. It donates a proton each time, meaning it is a polyprotic acid. Next, we look at auto-ionization or autoprotolysis. This is the ionization of water with water. So we have H2O plus H2O. One of the H2O molecules will act as an acid and the other as a base. We get H3O plus OH minus. Occasionally, one of the hydrogen ions from one water molecule leaves and bonds to the lone electrons of another molecule. Hydronium and hydroxide is thus formed, as shown here. We have an equilibrium constant for water, which is H3O plus, our products, and OH minus, and at 25 degrees Celsius, it is a constant value of 1 times 10 to the negative 14. Now, they will sometimes give you a question where they say at 25 degrees Celsius, the concentration of H3O plus ions is this. Calculate the concentration of OH minus. You will then use this as your basis to work that out, and you would put Kw as 1 times 10 to the negative 14, sub in the value for the concentration of H3O plus, and solve for OH minus. In the same way, they may give you OH minus, and you must solve for H3O plus. Moving on to the pH of a solution. pH is the measure of H3O plus ions in concentration at equilibrium. H3O plus ions are an indicator of acidity. So an acidic solution will have a greater concentration of H3O plus ions than OH minus. OH minus is an indicator of basic solution. For an acidic solution, you will have a pH less than 7. In a neutral solution, your H3O plus ions will be equal to your OH minus ions, and your pH will be 7. In an alkaline solution or a basic solution, your H3O plus ions will be less than your OH minus ions, and your pH will be greater than 7. Now here is an example of how to work with the water equilibrium constant at 25 degrees Celsius. We are given H2O plus HCl at 0.01 mole and H3O plus at 0.001 mole plus Cl minus. We know that Kw is equal to this from above. We know that Kw is 1 times 10 to the negative 14. We know that the concentration of your H3O plus is 0.01, and therefore we can solve for OH minus, which is 1 times 10 to the negative 11. Next, something that they like to ask in this section is indicators. You must know that an indicator is a weak acid, and they are used to show whether a solution is acidic or basic. The way in which an indicator works is shown over here. We have HIN, shown as our indicator. It ionizes to H plus ion minus. If you add an acid into this solution, your H plus increases. Your equilibrium therefore moves left. Adding a base decreases your H plus, as OH minus forms H2O with these H pluses. Therefore, your equilibrium moves right. The shift in equilibrium causes a change in the color of the indicator, and this is how we determine whether it's basic or acidic. These are some of the indicators that you should know. They do not come up often, but they are useful to know if they do come up and you need to know the name of them. Methyl orange you would use if you had a strong acid and a weak base. Litmus you would use in any cases, but you would use these more specific indicators where possible. Bromothiamyl blue you will use with a strong acid and a strong base, and phenylephthalene you will use a strong base and a weak acid. Now if we look at acid-base reactions, which form a large part of this section, you will need to know every one of these reactions off by heart. You will need to know that an acid plus an active metal, such as HCl plus magnesium, will form a salt, MgCl2, and hydrogen. You will need to know that an acid plus a metal oxide, such as HCl plus Na2O, will form a salt, NaCl, and water, H2O. You will need to know that an acid plus a metal hydroxide, such as HCl plus NaOH, will form a salt, NaCl, plus water, H2O. And then the most complicated one, you will need to know that an acid plus metal carbonate, H2SO4, plus Na2CO3, will form a salt, Na2SO4, plus carbon dioxide, CO2, plus water, H2O. Next, we move on to the hydrolysis of a salt. Hydrolysis of a salt is the reaction of a salt with water where water is decomposed. The salt can react with water to form OH- ions, which means it's basic, or H3O plus ions, meaning it's acidic. Salts that produce neutral solutions will come from the anion of a strong acid and the cation of a strong base. If we look at the salt KNO3, it will ionize into K plus NO3 minus. K plus, we can assume, would have come from KOH, which is a strong base. Therefore, K plus is a weak conjugate acid, as shown here. If we look at NO3, we know that would have come from HNO3, which is a strong acid. Therefore, NO3 minus is a weak base. When we put these in water, a weak acid being K plus and a weak base being NO3 minus, neither will react, leaving a neutral solution, a neutral salt. Salts that produce acidic solutions, salts from a reaction of a strong acid and a weak base. If we look at this, NH42SO4 will form NH4 plus SO4 2 minus. NH4 would have come from NH3 being a weak base to form NH4, and H2SO4 would have given us our SO4. H2SO4 is a strong acid, therefore SO4 is a weak base. NH3 is a weak base, therefore NH4 is a strong acid. If you haven't noticed, you take your beginning, if it's a strong base, you're going to be the opposite, therefore weak acid. In the same way, if it's a weak base, you're then going to have a conjugate strong acid. In a case like this where you have a strong and a weak, one being strong and one being weak, the strong one will always react. Therefore, we take NH4, the strong acid, plus water. Because it is an acid, it will donate, becoming NH3. And water will be a base, accepting a proton, becoming H3O plus. The concentration of H3O plus increases, which is an indicator of acidity, and therefore it is an acidic solution. Salts that produce basic solutions come from a strong salt from a weak acid and a strong base, such as NaF will break up into Na plus and F minus. We know that Na would have come from NaOH, which is a strong base, therefore Na plus is a weak acid. HF would have given us the F minus. The HF is a weak acid, therefore F minus is a strong base. Now we take the strong one of these two, which is F minus, and we react it with water. F minus plus H2O. If this is a strong base, it will accept, as shown here, it will become HF, and H2O will be an acid donating a proton, becoming OH minus. OH minus, as said before, is an indicator of a basic solution, and therefore the solution would be basic. In summary, if we have a strong acid plus a strong base, we will form a neutral salt. If we have a strong acid plus a weak base, we will form an acidic salt. And if we have a strong base plus a weak acid, we will form a basic salt. An acid plus a carbonate form a salt, CO2, and H2O. That is the most complicated acid-base reaction that you will need to know. Now here is an example just to go through how to work out whether your solution would be basic or acidic. If we take Na2SO3, when placed in water, this would break down into Na plus SO3 minus. We know that Na plus must have come from NaOH. We take NaOH and we break it down into Na plus and OH minus. NaOH is a strong base, therefore Na plus, as we see here, is a weak acid. We know that SO3 must have come from H2SO3, which is a weak acid. Therefore, SO3 will be a strong base. Now, out of these two, this is a weak acid and this is a strong base. So we take the strong one out of the two and we put it in water to see how it would react. We take SO3 minus, being the strong base, plus water to form H2SO3, as SO3 is a base and will accept the proton, and water as an acid will donate a proton, giving OH minus. OH minus is an indicator of a basic solution, and therefore your solution would be basic. Please keep an eye out on the YouTube channel for questions and answers and examples that we will be uploading. This is a section where you do need to practice a lot and get a hang of it. So we will be uploading a number of questions, examples, tutorials. Please keep an eye out for that.